Sir.
You can see the screen.
Yes, sir.
Okay. Any questions from yesterday? Okay. This
No,
is
sir. Stable and unstable equilibrium. Can you please explain it again, sir?
which one?
The potential energy.
Okay.
Stable and unstable equilibrium.
Okay. This one?
Yes, sir.
Okay, just a minute. Okay. So there is a torque acting on this dipole, right? So this is the plus Q. The force is towards right. Minus Q, the force is towards left, because the direction of electric field is towards right. Positive charge, the direction of force will be same as the electric field. Negative charge, the direction of force will be opposite to the electric field. Okay. So this Q will experience a torque in which direction? Clockwise or anti-clockwise?
Clockwise.
About the center point. Okay.
Yes, sir.
This minus Q will experience torque in which direction?
Anti-clockwise.
Clockwise.
Oh, that is clockwise. Okay, clockwise.
It's about the center point, because if you have two masses, equal masses, and when it is rotating, it will rotate about the center of mass. And center of mass is the center point here, O. So about the center point, if there is a force towards left, it will rotate in this direction. So both these torques are clockwise. Okay. So in theta equal to 0, positive charge is here, right? Negative charge is here.
Yes, sir.
Of the dipole. So from this position, if I try to move this, try to displace this thing little bit in this direction, okay, this clockwise torque will bring it back to this original position.
Yes, sir.
Okay, similarly, if I try to put it this way, displace it this way, when plus Q is here, it will produce an anti-clockwise torque. Because this plus Q, when it is downwards, again the force will be towards the right. Okay, the force towards right below this point will produce an anti-clockwise torque. Okay, the red arrow I showed because the Q is on the top and minus Q is on the bottom. When I displace it downwards, plus Q will go downwards. In that case, the torque which is acting will be anti-clockwise. So from this equivalent position, if I push it in a little bit on this side or on this side, both the sides, the torque which is acting will bring it back to the original position. So theta equal to 0 corresponds to stable equilibrium. Is that clear?
Yes, sir.
Okay.
Yes,
So
sir.
exactly opposite for the other side. Okay. In case of this one, theta equal to 180 degrees. So P should be in this direction. So negative charge is here and positive plus Q is here. Okay. So from this position, if I try to displace it slightly this way, okay, the minus Q here will have a force in this direction, right?
Yes, sir.
Okay. That will still take it further away.
Yes, sir. Anti-clockwise.
Okay. So this red arrow is not valid for this also. It was only valid for the previous one. Okay. So similarly, if I displace it the downwards, then also it will be. If I displace it a little bit downwards, then the negative thing will come here. So negative thing will experience force this way. So this will produce a torque in this direction. So we'll take it away from the equilibrium position. Theta equal to 180 degrees unstable equilibrium. Okay, is it clear?
Yes, sir.
Okay, so this is in terms of understanding in terms of torques. Similarly, in terms of energy, if the potential energy is minimum, then it means it's stable. This is basic understanding of potential energy that you have come in chemistry also. The equivalent position is the position in which the potential energy of the system is minimum. So potential minimum corresponds to theta equal to 0 degrees, because potential is minus P dot E, and minus P dot E is minus P cos theta. So when cos theta is plus 1, U will be minimum because of minus sign here.
Yes, sir.
Okay, and so minimum potential energy is corresponding to 0 degrees. That is same as the understanding we got here. 0 corresponds to stable equilibrium, and exactly opposite for 180 degrees. 180 degrees.
Yes, sir.
Okay, all right. So the two important things for dipole is torque is P cross E, and potential energy is minus P dot E. And what is the assumption here?
Potential energy at 90 degrees is taken as reference.
No, electric field is uniform.
Okay.
Okay. Otherwise, it will become complicated. Then there will be some net force also in addition to torque. It will be a little bit more complicated.
Yes, sir.
Okay. Now, if so, point charges, system of point charges, dipole, all those things are made of point charges. So now, if you want to make it continuous charge, one way of getting a continuous charge is like a line charge. So this is the line charge, like this. It's a curved line, but it's a one-dimensional charge, and we can have a surface charge like this, or we can have a volume charge. Okay, if these charges are not point charges, they are continuous charges. So this thing we can solve by taking small element of it. For the line charge, you take a small length element. Since the element is very small, it can be considered as a point. And for a point, you know how to calculate the electric field. So calculate the electric field with a small element and then integrate around the length of this thing. Similarly, here take a small area element, and here takes small volume element, and then you have to integrate over the surface or over the volume to get the net electric field. This is what I've said here for volume element. For the small volume element, the charge will be rho into dV, right? So K is 1/4 square. The charge by distance square, that is the electric field due to the small element. To get the total electric field, you just have to integrate it over the entire volume. Similarly for surface charge and also line charge. Okay, so now we consider a ring. Ring is like this. So this is a line charge or a surface charge or volume charge. Is this the line charge or surface charge? Ring?
Line form.
Yeah, because it's only on this circumference, so it's like a line. So to take a small element here, the electric field will be in this direction. It's radially outward from the element, so it will be in this direction. So, and if I take another element which is diametrically opposite, see here, the electric field due to this will be in this direction.
Yes, sir.
And what about this angle? What is this angle? This angle I marked as theta. So what is this angle? It's theta. And what about this angle? That is also theta by symmetry, because this element also, if I draw a line like this, okay, so this angle is also theta.
Yes, sir.
That is by symmetry, because this is a ring and this line is perpendicular to the plane of the ring. Otherwise, it will become complicated. Okay, so in this situation, there is symmetry, so everything is simple. So if I take these pair of elements, the components which are perpendicular, they will cancel.
Yes, sir.
Only the horizontal component will add. So two of them are there. So electric field magnitude is 1/4 epsilon dq by r square, where r is this distance of the element from the point where I'm finding the electric field, and direction is r cap. R cap direction is, okay, this is a temporary direction, which is this one for this one. So the cos component will add. So it is cos theta, and then, okay, so dq is the charge of this two pairs. So, okay, and cos theta is also constant. If you take second pair like this one here, and the diametrically opposite here, for this element also, the angle made by this line with this line is theta. This angle is also theta. Is that clear? Because this line is in the plane of the paper, this out of the plane of the paper. You should visualize in 3D. This is a cone. So all these lines are on the surface of the cone. This line is also on the surface of the cone. This line is also on the surface of the cone. So both these lines are similar. So all these lines which are on the surface of the cone will make a same angle theta with the axis of the cone. Okay, so any element, everything will have same theta. So now if we integrate this one, everything is constant here. X is also constant. The only variable is q. And that q, dq is also same for all the elements. So integral dq is total q. So the electric field will come out as 1/4 the charge by distance square, that is r square plus x square, into cos theta, because all the cos components will add, and cos theta is x by square root of r square plus x square. So for remembering this formula, you can reverse 1/4 charge by distance square. Distance square is r square plus square, and then you take cos theta, and cos theta is x divided by square root of this one. Is that clear?
Yes, sir.
Okay, I'm just telling you a way of remembering this formula. For a point charge is q by r square, right? The distance square, and the distance is this one, r square plus x square. Okay, and then I take the cos component. So this cos component is x divided by square root of this one. That's why we have a power of 3/2. Okay. So extreme case, when x is 0, x is 0 means it's at the center point, right? In the plane of the disk. Yeah. So in that case, what will be the electric field here?
Zero.
Huh?
Zero, sir.
Why will it be 0?
Because the formula says
Yeah, that is one way of understanding. Another is it's electric field is force acting on a unit positive charge kept here, right? So this element here and the diametrically opposite element here, they will give force in opposite directions, and they are equal forces. So they will cancel. Okay.
yes,
So
sir.
similarly, if I take another pair, one element here and one element here, they will give force in opposite directions. Okay. So that we can get from this formula also. If you put x equal to 0, electric field is 0. So another extreme case is if x is very, very large. When x is very, very large, what will be the electric field?
X is very, very low.
So this point,
It will be like a point charge electric field, sir.
yeah. So x is very, very large means I can neglect this r square. Okay. So this thing will become x cube. So one x will cancel, will become q by x square. That is like a point charge. That makes sense, right? Because when I go very, very far, this whole thing will look like a point charge.
Yes, sir.
Okay.
Yes, sir.
So the only thing you have to remember this formula. For remembering this formula, I told a trick. It's q by r square, where r is the distance, and then cos component, which is x by square root of this one. This distance is square root. Okay. Similarly for a disk. So this is a surface charge or line charge.
Surface charge, sir.
Okay. So now again we have to take this disk. We can consider as made of a lot of rings. Okay, so I'll take a ring at a particular radius r. Okay, and electric field due to a ring we have formed here, that this will use there. So electric field due to a ring is kx, k into charge, and this charge is charge of the ring, and this charge of the elemental ring is dq. Dq divided by the distance square, that is r square plus x square, into cos of it, that is x divided by square root of r square plus x square. So this is due to a ring of radius r. Okay, so now 2 and dq I can write as this one, 2 pi r. dq is basically the area of the ring into the surface charge density, sigma. Okay, and area of a ring is 2 pi r dr, elemental ring. It's this, you know, right? It's circumference 2 pi r into the thickness, dr.
Yes, sir.
Okay, so now there is only one variable here. And what is that variable?
That is,
X is constant because point P is fixed. R is the radius of the ring. So this R will vary from 0 to capital R, which is the outermost radius. So R is a variable here. So I have to integrate this thing from R, small r varying from 0 to capital R. So this is a standard equation. Numerator we have R dr, and here it's asked us. So I have to put a variable substitution, this one. So from this we come R dr as du. So this integration is simple. U raised to the minus 3/2. So it will become like this. And then I have to put the limits. Okay, and I'll get this one. So electric field here is sigma by 2 epsilon naught into 1 minus x divided by this one. Okay.
yes, sir.
So extreme case, x is approximately 0, so that's very, very close. I'm not putting it 0. Previously I put it 0. Okay, here I cannot put it 0 because when I go close to the charge, electric field go to infinity. Because electric field is given as 1 by 4 for a point charge, q by r square, right? So previously there was no charge here at the center. So I can go close to, I can go to x equal to 0 itself. But here I cannot go to x equal to 0. I'll be in trouble. So I'll go very, very close to 0. That means x is very small. In that case, so this I can neglect. So denominator will become 1 by r, and x is very small means I can get from this one. X is very small means I can neglect x, so it will become 1 minus x by r. 1 minus x by r, and x is very small, right? So this term is neglected. So it becomes sigma by 2 epsilon naught, and this is like an infinite sheet. You know electric field due to infinite charge sheet.
Yes, sir.
So when you go close to this one, it's as if the sheet is infinite because you won't be able to see very far from here.
Yes, sir.
Is it clear?
Yes, sir.
Okay. So it is consistent with that formula, sigma by 2 epsilon. So one way of remembering this formula is sigma by 2 epsilon naught, that is 2 for infinite sheet. And after that, there is a factor here, 1 minus x divided by square root of r square plus x square. Okay.
Sir, electric field due to disk, is that included in syllabus, sir? NCRT.
It's not there for you. Okay, it's not there in NCRT. Okay, fine. So ring is there.
Yes, sir. But we
Okay.
never studied that.
Okay, I am more familiar with GE syllabus. Okay, fine. Then you can leave it. You don't have to give too much importance to that.
Yes, sir.
So electric field charge arc. So this is a part of a ring. It's not a full ring, and it's in the center of that. If you complete this ring, it will be at the center. So here also electric field I can find by taking an element here. So the electric field in this element will be along this direction D, and this arc will have a center point. Okay, so with that center point, it will make an angle theta. So if you take another pair here, which is symmetrically placed on this side, and if you consider electric field due to this pair, only this component along the middle line will contribute. The perpendicular component will cancel. Okay, and d is k dq by dr r square. This is clear. R is the radius of distance from this to the center, and dq is the charge of this element. This is clear, right? Yes.
Yes, sir.
Okay, and dq is the fold charge is distributed along this angle of say phi. So it is phi divided by q divided by phi into d theta. Because this fraction is d theta, this small element is making angle d theta, and this fold line charge is distributed over an angle phi. So the amount of charge present in this angle d phi is q by phi into d theta. Okay, so cos component of this electric field contribute. So dE cos theta, and dE is this one, k dq by this one, and dq you put in terms of d theta and cos theta. So here there is only one variable, theta, and theta is varying from minus pi by 2 to plus pi by 2. This is the reference for theta, theta equal to 0. And for this reference, theta will vary from plus, here it is minus 5 by 2, and here it is plus 5 by 2. And integral of cos theta is sine theta, derivative of sine theta is plus cos theta. So integral of cos theta is plus sine theta. Putting the limits, I'll get like this. So I think you can also leave this one. I think it may not be important for you. Okay, line charge of a finite length. So I can take a small element here, and we'll have two components. One is cos theta along the y-axis, and other is along the x-axis, sine theta. Because I'm taking this angle as theta, so this angle is again theta. No. This angle is theta. So d cos theta is along y-axis, and sine theta is along the x-axis. So dx is d sine theta, and d to the small element is k into dq by distance square. It's x square plus r square. R is constant, but x will keep changing. X is a variable, sine theta, and dq is q divided by length into dx. dq is q divided by length, the full length, into the elemental length dx. Is that clear?
Yes, sir.
dq is this charge of the small element. So the full charge is spread over this length L. So per unit length will be q by L into the length of the element dx, that will be dq. So this is a variable. The only variable is, okay, x and theta I can relate. X is r tan theta. This is x. If I take tan theta, it will be x by r. From there I get x to r tan theta. So dx I can write in terms of d theta. So instead of dx, I'll get it in terms of d theta. So this will be the expression. It's sine theta, d theta. So to get the electric field in x direction, I have to integrate this one. The only variable is theta. And theta will vary from minus theta 2 to theta 1. This is theta 2, and theta 1 will correspond to this angle. So this is the final expression. Similarly, I take the y component. So y component, the difference is instead of sine here, it will be cos. And the magnitude of the electric field is same. And so it will be cos theta d theta, and then I have to integrate this one with the same limits. So I'll get this one. So it has got electric field in x direction, also in y direction. So in the special case of theta 1 and theta 2 being same, suppose this is the thing, and I'm finding electric field at the middle point, which is equally. So in this case, the electric field will be in the only in the y direction. X direction electric field will cancel. Is that clear? When this extreme theta 1 and theta 2 are same, only electric field will be in the y direction, because if you take a parallel elements, one here and one here, the electric field due to this one will be in this direction, and the electric field due to this one will be in this direction. So only the vertical component will add, and the horizontal component will cancel. One will be in the plus x, and another will be in the minus x. So when theta 1 equal to theta 2, ex is 0, and ey is along the positive y direction. So when theta 1 equal to theta 2, cos theta minus cos theta is 0. Here it will become 2 sin theta. Right? Is this if there for your NEET thing?
No, sir.
Okay. Okay. This is electric field is a charge ring. Okay. So this is a function of x, right? Capital R is the radius of the ring that is fixed. So only x is a variable. So what will happen when x is 0? Electric field is 0, right?
Yes, sir.
At x equal to infinity,
In that case also electrical will become 0, sir.
so electric field will look like this. At very large distance, instead of x, I have put r. This should actually be x. So electric field is 0 at x equal to 0 and also at very, very large distance. So somewhere in between it should become maximum. So it will become maximum
Yes.
at 0.7 r, where capital R is radius of the ring. So on the negative side, it will be exactly same, but the direction of the electric field will be opposite direction. That's why it's shown as negative. One of the directions I am taking as positive. So positive x is positive electric field, and this negative x is in the negative direction, so it's shown as negative. Okay, this is there, I think, in your syllabus because it's due to a ring, and you can get this by differentiating this function
Yes,
of
sir.
x. So if you differentiate this thing with respect to x and put it equal to 0, you get x as r by √2, which is approximately 0.7. And the value of maximum electric field you can find by putting this value of x. Right. So next is Gauss's law. So concept of electric flux I've introduced, right? Electric flux is nothing but through electric flux through a small element is integral E dot dA. Okay, and E dot dA is E into dA into cos theta. So this is to a small elemental area dA. If you want to get to a bigger element, what I have to do? I have to integrate.
Yes, sir.
Okay, so that is the concept here. So to get, when you're studying Gauss's law, you're taking a completely closed surface. So Gauss law says that if you have a closed, this is a closed surface. You know what's a closed surface and open surface, right? When you have a closed surface, there will be two regions. One is inside, another one is outside. Okay, but if you have an open surface like a disk, okay, there is nothing like out and in. Getting the idea, right?
Yes, sir.
If you have
Yes, sir.
if you have a ball, you can see, you can clearly see some which point is inside, which point is outside. But if you have a disk, okay, then it doesn't make sense to talk about in and out.
Yes, sir.
Okay, so here we are considering closed surface. So in the integral sign, if you put this circle, it means it's closed surface. Okay, this you know, right? On the integration sign, if you put a circle,
Yes, sir.
it means closed surface. So it means integral E dot dA. This integration is over a closed surface area. That's equal to Q by epsilon naught. What is Q here?
Charge of the entire.
But which is inside. You just have to take only the charges present inside. Okay,
Yes.
if there is some charge here, you don't have to take that one. Okay, only the inside charges you have to take. So this is Gauss's law. So integrate over the closed surface, and Qn is the total charge which is present. Here I written as Qn. Okay, and this chosen surface of integration is called the Gaussian surface. So the electric field to the infinite wire I can find by using Gauss's law. So this is an infinite wire which is going to infinity on up and down. So here I am taking a cylinder. The axis of the cylinder is same as the coinciding with the line charge. Okay, so the electric field due to this one, how will it look? It will be radially outward. This is by symmetry argument.
Yes.
This you have to get by symmetry argument. There is no other way. If you want to do it strictly, then you have to do by Coulomb's law. We got this by Coulomb's law here, right? Okay, in this you have to put theta equal to 90 degrees. This infinite line charge corresponds to theta equal to 90 on this side and also 90 on the other side. So when you put theta equal to 90, so when you put theta equal to 90, so cos 90 minus cos 90, this will become 0. and sine 90 is 1. So this will become 2. Okay, so 2 times this one, and it's only Ey. Ex is 0. So Ey means it's in the radial direction. This is the y direction. So that means the electric field is radially outward. If you take,
Yes, sir.
okay, so you got the idea, right? So you have to have that prior knowledge to solve this problem by Gauss law. So electric field is always radially outward. There is no other direction. So this electric field, will it cut this top surface and bottom surface?
Top side. No, sir.
It will
Touch that.
just touch it. It will not cut it. But on this curved surface, it will cut it.
But
Okay.
we have to take that area vector only, no, sir.
Yeah. See, for this curved surface, this is the area element.
And the area vector also parallel to the electric field.
Yeah. Whatever element you take, the radial electric field will come out perpendicular to it. It will come out like this. I'm not drawing it properly, so you have to visualize. So if you take an area element here, it will be like this. So we'll cut that area 90 degrees. Even this element.
No, sir.
Huh?
And that surface, that
Yeah.
electric field is parallel to that area vector, no, sir.
No, on the top surface it is parallel, top and bottom.
No, on the top it will be perpendicular to the area vector, no, sir.
Yeah. Sorry. Yeah. The area vector is like this. Yeah. What I meant is to the surface. To the surface it will be parallel. To the area vector, which is normal to the surface, it will be perpendicular. Here the area vector is this way, and also the electric field is in the same direction. Even for this one, the area vector and the electric field vector both are in the same direction. Okay. So for the curved surface, this angle is 0 on the curved surface and 90 degrees on top and bottom surfaces. The angle between the electric field and the area vector, elemental area. Yeah, it's area vector. So only the curved surface will. So this integral over the whole closed surface will become integral over only the curved surface. Okay, and this electric field on the curved surface is uniform by symmetry. This is also by symmetry. This is clear. Okay, so E can come out the integral sign. Integral dE is the total surface, curved surface of the cylinder. There is 2 pi r into L. Okay. Q into epsilon naught, and this Gaussian cylinder length is L. L is arbitrary value. So once the length is fixed, the charge inside is lambda into L. The lambda is the linear charge density of the wire. So from this I get the electric field as lambda by 2 pi epsilon naught into R. So this formula also you have to remember. Okay. So lambda is a linear charge density.
Yes, sir.
Okay. So electric field is going as 1 by R. But dimensionally it is by R square only because here it's a linear charge, right? Linear charge is Q by R. So that Q by R and this R will combine to give dimension as R square. So the dimension of this full thing is still Q by R square only. This lambda has got a dimension of Q by R. So that R will combine with this one. So dimension of this thing is Q by R square. So this formula you have to remember. So similarly, I can find electric field to be an infinite sheet. This is infinite. If it is not infinite, then it will become complicated. Here also this line charge is infinite. Only then this thing will become radially outward. That will become complicated. So here we check the Gaussian surface as the same cylinder, but in this case, the electric field will cut through the bottom and top surfaces, not through the curved surface. Because electric field to be infinite sheet will be sigma by 2 epsilon naught and will be normal to the infinite sheet. So this electric field will cut through the top and bottom surface. Is that clear?
Yes, sir.
And that electric field value is sigma by 2 epsilon naught. So applying Gauss's law, where the whole curved surface can become only on the top and bottom surfaces, only on top and bottom surfaces. So E will come out, and E is uniform everywhere because it's in the infinite sheet. Okay. So since E is uniform, it will come out the integral sign, and this area is both top area and bottom area. So that's why it becomes 2 into A. So from this we get electric field as sigma by 2 epsilon naught, and the direction is normal to the surface. Okay, this is the easy to remember, and you already know sigma by 2 epsilon naught. It's an infinite sheet, otherwise it will be a problem. So there is a conceptual question. What is the advantage of using Gauss's law? You already know this answer. See, you can see for this thing, for infinite line charge, you can find electric field either using Gauss's law that we have done here, or using Coulomb's law. Okay, and in the Coulomb's law, you have to put theta equal to 90 degrees. So which one is easy to calculate? Gauss law, because the integration becomes trivial here. The trivial integral dA, which is there the integration was a little bit complicated. So to avoid integration means to avoid complicated integration, we can find electric field using Gauss's law. Actually, Gauss law and Coulomb's law are equivalent in the sense you can find electric field using Coulomb's law and also using Gauss law. But Gauss law can be used only in certain cases where there is symmetry. In the case of infinite wire, there is a cylindrical symmetry. In case of infinite sheet, the electric field is uniform, both above the sheet and below the sheet. So in special cases, Gauss's law can be used where the integration becomes trivial. Okay, so similarly, I can find electric field to be a point charge using Gauss law and also Coulomb's law. Okay, so this is a point charge. So to find electric field at a point at a distance r, I take a spherical surface. So this is my Gaussian surface. So d phi is E dot ds, that is E into ds. The electric field direction is radially outward, and also the area vector is radially outward. So both are in the same direction. So E dot ds is the same as E into ds. To get the total flux, I have to integrate this one. So integral E dot, and E is uniform, so it will come out the integral sign. And integral ds is surface area of sphere is 4 pi r square. This you know, right? Okay.
Yes, sir.
And by Gauss's law, the flux is q by epsilon naught, where q is the charge inside. So from this, I get the electric field as 1 by 4 pi epsilon naught q by r square. So this expression for electric field for a point charge is got from Gauss's law. Same thing is got from Coulomb's law. Okay. So
Yes, sir.
in some sense, Coulomb's law and Gauss law are equivalent. But Gauss law is useful when there is some symmetry. Okay, the electric field components, Ex is alpha x to the power half, Ey and Ez are 0, and alpha is some value given here. Calculate the flux through the cube and the charge which is present inside the cube. So the cube is kept, assume E is 0.1 meter. Okay, the cube is kept at x equal to A. Yes. So this point is x equal to A, and this point is x equal to 2A, because value of x is required because electric field is dependent on x. So is this uniform electric field or not?
Non-uniform.
Non-uniform because it's dependent on x. So here the electric field is in x direction because only Ex is there. Electric field is Ex I cap plus Ey j cap plus Ez k cap. So Ey and Ez are 0. So electric field is always in the x direction. So the flux will cut only left and right phases. The remaining 4 phases, the flux is 0. Okay.
Yes, sir.
So the flux of the left phases, this one, where the value of x is constant and the value of constant value is A, because left phase is x equal to A. So this is the value, and this minus 1, how we got? It's E dot dA, right? So the area vector is outward, and electric field is outward, and it's in the left. Electric field is towards right. So theta is 180 degrees, cos 180 is minus 1. So that's why this minus sign. Okay. And for the right phase, both area vector and the electric field vector are in the same direction. So cos 0 is 1. Is it clear?
Yes, sir.
And value of x is 2a. Similar problem we solved yesterday. So,
Yes.
when flux through the cube is flux through only the left and right face, remaining 4 phases the flux is 0. So adding these two we get this one. Okay, and value of a is given. And for now using to find the charge inside, we have to use the Gauss law, because we flux through the cube we have found out just now. And using the thing we can find out how much charge is inside. So charge inside is this one. Okay. By Gauss law, we can relate the charge which is present inside the closed surface to the flux that is coming out of the surface. So flux coming out of the surface we already found out. So using that we can get charge which is present inside. In some sense, Gauss law is relating the charge inside the surface and the flux cutting that closed surface. Like Coulomb's law is giving relation between the charge Q and the electric field. Here it's giving the relation between the charge present inside the surface and the flux that is coming out of the closed surface. Okay. A point charge is kept at the corner of a cube, which is shown here. What is the electric flux through each phase? So, can you? So, what is the electric flux that is passing through the top phase?
0, sir.
What about this phase? The right phase?
0.
Similarly, the back phase is also 0, right?
Yes, sir.
So 3 phases, it's just the electric field lines will just touch the surface, will not cut through them. But remaining 3 phases, which are marked in the green here, and the pink here, and the orange here, they will cut the electric field lines. Okay, and all these the 3 surfaces are symmetric from Q. Can you visualize that? All these 3 surfaces, green, pink, and this orange one, they are
Yes, sir.
they are equal for this point charge. There is no difference between these 3 phases. So, and this total flux that is coming out of this point charge Q, 1/8 of them will pass through this cube. That we can visualize by, this is a cube I have drawn here, and similar to this cube, I can add 3 more cubes on the front side and 4 cubes on the back side. This one is clear, this figure is clear. This colored cube is this one. Okay, so similar to this cube, I can add 3 more cubes on the front side and 4 cubes on the back side. Is that clear? Yes? Yes or no?
Yes, sir. The charge Q is carried by 8.
Huh. Okay, like if you have x axis, y axis, and z axis, that will positive x, positive y, and positive z will give 1 quadrant, right? So total there are 8 quadrants.
Yes, sir.
In a 2D, it's four quadrants. In a 3D, it's 8 quadrants. Okay, so the charge which is electric field lines which is coming out of this cube will be 1/8 of the. It's just 1 quadrant, so it's 1/8 of the total flux. And total flux which is coming out of this charge is Q by epsilon naught. This is by Gauss law. Okay, and 1/8 of them will pass through this cube. Okay, the total flux coming out of this cube is 1/8 of the total flux that is coming out of this charge, that is Q by epsilon naught. And flux that is coming out of any one of the phases, 1/3 of the flux that is coming out of this cube, because all these 3 phases are equivalent for this charge. So it's 1/3 of the flux that is coming out of the cube. So 1/8 into 1/3 of 1/8 is 124. 124 the total flux. So this is the flux that is coming out of these 3 phases, and remaining 3 phases is 0. Is that clear?
So flux by the Q is shared by 8 cube. So for each cube, it is divided by 1/8.
No, the total flux that is coming out of this Q is Q by epsilon. That you know?
Ah.
I can just draw a small sphere here and cut flux coming to the sphere by Gauss's law. I can get as Q by epsilon. So total flux coming out of this charge Q is Q by epsilon, and 180 of them will pass through this cube because there are 8 cubes, and this is one of the eight cubes. So this is clear.
Yes, sir. That's what I'm
Okay, and these 3 phases are equal for this charge Q, and remaining 3 phases, nothing is there. So these 3 phases are equal for this thing. So to any one phase, it will be 1/3 of the total thing that's coming through this cube.
Yes, sir. Yes, sir.
Okay, and 13 into 18 is 124 of the total flux coming out of the charge cube.
Yes, sir.
Okay, so it's 124 of the total flux coming out of the charge. Clear?
Yes, sir.
And flux to the adjacent phase is these ones, that is 0. Okay,
Yes, sir.
so here there is a pot. The point charge is present inside at a distance at the depth of h. So an opening has it's a circular disc or opening which the radius r. Electric flux through the surface of the container. This also we can obtain by Gauss's law. So electric flux through this entire this curved surface plus this disc or the opening. What is the total electric flux coming out of this entire surface? It's Q by epsilon naught, right? It's a point charge.
Yes, sir.
Total flux coming to the point charge is Q by epsilon naught. So all this flux will either pass through this curved surface or the top opening. So if you consider both of them together, and what is the flux that is passing through this circular disc? That I have got a formula here.
Lengthy formula.
Okay, and this x divided by root of x square plus r square is cos of this angle. Suppose I call this angle alpha. So this is cos alpha. So it's sigma by 2 epsilon 1 minus cos alpha. Where alpha is the angle of this cone. You can assume that there is a cone that's formed by this point. So the flux that is coming out of this opening is q by 2 epsilon 1 minus cos alpha, and alpha is here h divided by root of h square plus r square. Because this is the angle. Okay, and cos of this angle is this distance, that is h, divided by the hypotenuse square root of h square plus r square. So this is clear. This is the flux through the opening. Okay, so, and flux through the entire surface I know. So the flux through the container is the curved surface, is the total flux minus the flux through the disk. This logic is clear. Okay, so from this I'll get the flux through the container surface. It will become 1 plus.
Okay.
If I add this flux with the container surface and the flux through the opening, okay, it should give me q by epsilon naught. Okay, so when I add these two, this term will cancel, and q by 2 epsilon naught will add to q by epsilon naught. So that is by Gauss law. That is the total flux coming to the point charge. Okay. Okay, so special case I have put r equal to 0. R equal to 0 means all the flux coming to the container surface will be the total flux coming to the point charge. So if you put r equal to 0 here, this will become 2, right? If you put r equal to 0 here, this thing will become 2.
Yes, sir.
So flux to the container surface will become total flux of the point charge. Okay,
Yes, sir.
so another extreme case is h equal to 0. What will happen when h equal to 0? So this point charge is coming here, right? On the surface, on the opening. So what is the flux in that case passing through this container surface? Half the flux, right? It will be half the flux.
Half. How could you say?
Because the point charge is kept here, half the flux is going out. Only half the flux is entering this pot. Got it? No, this point charge is this opening surface. So all the things which is on the upside will go out of the container. Only the downward flux will pass to this surface. Will get in the pot. So as you can get from this expression also, if you put h equal to 0, this second term will go. So it become half of Q by epsilon naught. For h equal to 0, half the flux will go out. And mathematically also, if you put h equal to 0, the second term will become 0. Okay, and become half of Q by epsilon naught. And Q by epsilon is the total force coming out of the surface. So when it is on the surface, only half the lines will be inside, right? Other half will go out. Is it clear?
Okay, yes, sir. Yes, sir.
So two large sheets of uniform charge distribution, find electric field at points A, B, and C. So this you already know. So what is the electric field at point A?
Two K lambda by D
No,
by
it's a sheet, no? So electric field coming out of the sheet is sigma by
2 epsilon naught. Constant.
Yeah, and it's infinite. Two large sheets. Okay. So it's approximately infinity. So at this point, at electric field at this point is what? Then A sigma by 2 epsilon naught, right?
Yes, sir.
Due to this one. Okay.
Yes, sir.
There will be electric field due to this other one also. So that will be sigma by 2 epsilon, but it is minus sigma. So the electric field will be like this. The electric field due to negative sheet will be like this.
Yes, sir.
And the electric field due to the positive sheet will be like this. So at point A, what is the net electric field then?
Sigma by epsilon naught.
So this into 2. What about electric field at point B? Somewhere outside point B.
Sigma by 2 epsilon naught.
That is due to this green one, and the orange one will be like this, right? See, this orange one is there everywhere. It's infinite sheet, no? So this
Cancel.
yeah. So the orange one will be here also. So electric field at B is what? 0. And what about electric field at C? 0. So this is what is happening in capacitor plate, no? Capacitor plate, all the electric field lines are inside. Outside, there are no electric field lines. And the capacitor plate, the distance between these two plates is very, very small. In that case, for a point inside, it's as if it's infinite sheet. Okay. Two large ones approximately infinite. So approximately there are no electric field lines outside. So electric field
Sir, in negative. Sir? In negative sheet.
Yeah.
The charge on that right side sheet will not account for the electric field on the left side, sir. That is towards the B.
At point C, the electric field with the positive charge is this one green one, and the electric field with this negative sheet will be this orange one. So these two will cancel right at point C. At point C, these two are there, this one and this one. See, it's infinite sheet, so this green arrow is there everywhere. Similarly, this infinite negative sheet, this orange arrow is there everywhere. So for all on the left side, the electric field is like this, due to the negative one. Right? So at point C, this thing will cancel. Similarly, at point A also.
Yes, sir.
So electric field is present only in between the space between the capacitor plates, not outside. Okay, and this capacitor plate, the distance between the two capacitor plates is very small compared to the size of the capacitor plate. That's why it's as if the sheet is infinite. So electric field in between it's sigma by epsilon naught, and electric field outside is 0.
Yes, sir.
Okay. This is there in NCERT, no? Yeah. Electric to a thin spherical shell. So thin spherical shell is the charge is only present on the surface of the shell and it's uniform, otherwise it will become complicated. So when there is some sort of a symmetry, here what is the symmetry? It's spherical symmetry. Spherical symmetry means things are depending only on the radius. There is no direction dependence. What is happening in this direction is also happening in this direction. So with respect to direction, there is no difference. Whatever is happening in this direction is happening in this direction, happening in the direction out of the plane of the paper. All the directions are same. Such a thing is called spherical symmetry. So in this case, I take a Gaussian surface, which is a spherical surface whose radius is greater than this radius of the shell, because I have to find electric field outside. So again, I can use Gauss's law, and electric field is uniform, right? By symmetry, electric field uniform is the magnitude. Direction is different. Direction is radially upward, and the angle between the electric field vector and the area vector is 0. Both are radially upward. So the angle is 0. So E dot dA is same as E into dA, and E uniform because it depends only on the radius, and radius is same for all the points on the shell on the Gaussian spherical surface. So E will come out, and this dA is trivial integration, that is 4 pi r square. And total charge present inside is total charge of the shell. So E into 4 pi r square is equal to Q. So Q is total charge of the shell. So from this I get the electric field as 1 by 4 pi epsilon Q by r square. This is for points which are outside of the spherical shell. This is like a point charge Q located at the origin. So for points inside the shell, so this is the shell. I'm taking Gaussian surface, spherical surface which is inside. So again we are applying Gauss's law. Here Q is how much?
0.
So that's why electric field is 0, because electric field is uniform, so it will come out. So 4 into pi r square will be 0. So E should be 0. So all points inside of the shell, electric field is 0. And for points outside, it's as if the full charge is concentrated as a point charge at the center. Okay. So for points outside the sphere, okay, it's as if a point charge located at the center. So this variation is 1 by r square, similar to a point charge.
Yes, sir.
And inside the electric field is 0. So only for outside, I would take it as a point charge, not for inside. Inside is 0, that comes independently. Outside, you just have to assume it's as if it's a point charge is there at the origin. Okay. So sphere is also there, no? Sphere is not there for you. No, this is not from NCERT. So I think I will leave it for you. Okay, I'll just give the idea. So for a sphere, you just have to take small elemental shells. You know how to find electric field due to a shell, right? Electric field due to a shell is outside of the shell, it's like a point charge. Inside of the shell, it's 0. So using that idea, we get outside of the shell, outside of the sphere, it's 1 by r square. And inside, we just have to take the amount of charge which is present inside this small r. This is the full sphere. If you have to find electric field at a distance r, only the shells which are within this radius small r will contribute. The shells here will have 0 electric field at this point. Is that clear?
Yes, sir. I will just remember that concept alone, sir. End result.
Yeah. So for a sphere, if you have to find electric field at this point, this sphere can be considered as a lot of spherical shells, and all the spherical shells, this point is outside. So all the shells I can consider as a point charge here. So this 4 of this sphere charge, I'll consider as a point charge here and find electric field at a point outside. But for point inside, these shells which are here, they will give 0 electric field to this point, because for all these shells here, it's as if this point is inside of the shell. So these shells which are here, outside of this small r, the electric field contribution is 0. But the shells which are inside, that will contribute electric field to this point. and this shells as if the four shell is constant at this point. So what I'll do is I'll take this four sphere and I'll calculate the charge of the sphere and concentrate the charge as a point charge here. Okay, so that's what is happening here. 4 by 3 r square into the charge density, that is the total charge here. So that charge, that is q into r cube by r cube divided by that charge divided by r square is the electric field at this point. Just take the concept. Electricity is very similar to charge. Okay, this also not there. Okay, so this question, this is a uniform spherical. Okay, charge is okay. So here is a hemispherical shell of radius r and volume density rho. Okay, this is a volume charge density. Okay, this can even be true for a, okay, so here is a spherical volume charge hemisphere, and the electric field at this point at a distance 2r is E. So this radius is r, and there is a point here which is at a distance r. Below. So I have to find the electric field at this point, which is a distance 2r from this center point. Okay, so this charge of plus rho, I can think of made up of the full sphere as plus rho and a negative hemisphere of charge minus rho. This is by superposition principle. I can take a charge q as 2q plus minus q. Is that clear? So this charge plus q, I can take it as sum of sphere of charge plus rho and a hemisphere of charge minus rho. So this minus rho will cancel this top, this one, and give me this one. So this one is clear?
Yes, sir.
Okay, so electric field at point B is the one I have to find out. So electric field at point B for this one can be got by electric field due to this one due at this point, and if you do this one at this point. This is by superposition principle. Electric field at due to this one at this point is given as this whole thing. I can assume as a point charge located at the center. So it's kq by distance square, kq by r square, and r is this distance 2r. And the electric field due to this thing is being given as E. The electric field due to this, it's given as E. So due to this minus rho, it will be minus E. Okay, so if I subtract this one, I'll get this one. Okay, so this is from NEET. So this is in your syllabus only. So two parallel infinite line charge density plus lambda and minus lambda are placed at distance 2r in free space. Electric field midway. You have pen and paper? Just try this one. You can straightaway use the formula for an infinite line charge. So it's lambda by 2 epsilon naught r.
2k lambda by r.
Lambda by 2 epsilon naught r. I think it's 2 pi, right? Okay, so there are two line charges. One is plus lambda and the other one is minus lambda, and midway. So the electric field due to this one, the direction will be this way, right? And electric field to this minus, this also will be in this direction. So this into 2 will be the answer. And the distance between them is 2r, so this distance is r. So that will cancel. So it's lambda by 5 7 not r. Got the answer?
Yes, sir.
Okay. Answer is 3. So it's readily outward the electric field direction and electric field due both of them will add. So okay, this one, toy car, charge moves on a friction with horizontal surface under the influence of electric field E due to force Q into E. Force on a charge Q in electric field is Q into E. That's what is written here. Its velocity decreases from this one in 1 second duration. At that instant, the direction of electric field is reversed. The car continues to move for 2 seconds under the influence of electric field. The average velocity and average speed of the toy car between 0 and 3 seconds, respectively, are. Electric field is uniform, so it is simple only. So electric field uniform is the force is uniform, right? When force is uniform, acceleration uniform.
Yes, sir.
So in some sense, acceleration and force
Sir,
are acceleration and force are same. It's just that it's multiplying by a factor of mass. So once force is known, acceleration is known. The velocity is increasing from 0 to 6 meters per second in 1 second. Okay. So from this, what is the value of acceleration?
6, sir.
Hold on, he's just asking average velocity and average speed, right? Okay, this something else is happening. The car continues to move for okay, it is getting complicated. Are you able to solve?
No, sir.
See, you have to find the velocity at this. See, after the 1 second, so after 1 second, the direction of the electric field is reversed. So after 1 second, t greater than 1 second, so the initial speed is 6 meter per second, and acceleration will be retardation, and the value of acceleration from here is 6 meter per second square, right? So here the acceleration will be 6 minus 6 meter per second square. Your car can just move for 2 seconds. So at t equal to 3 seconds, the velocity is becoming 0. Okay, and find the average velocity and average speed of the toy car. So here it is 6. Okay. Sorry. Okay, the direction is reversed now. Right. Okay, let me not waste time. I'll tell you next time. So this is what is happening. The velocity is increasing from 0 to 1 second. After this thing, the direction of the momentum is reversed, the direction of acceleration is reversed, but it continues moving in the same direction because it has got some initial velocity. But the velocity will keep on decreasing because there is a force in the opposite direction of motion. So it is between 3 seconds. So you have to find average velocity. So one way of getting the average velocity is total distance traveled by total time. Okay. So and then speed distance by time. So my assumption both should turn out to be equal. So this maximum speed is this is 6. So this area is how much? Half in the basic height. So another thing I can do is half basic the height is 6. So this is 9. That is the distance traveled 9 meters. 103 seconds. So 9 meters divided by the total time 3 seconds. It is 3 meters per second. Aha. And I'll tell you next time. To identify is having charge 10 to 10 are tied with two strings of equal length 1 meter apart at a common point. So it is very simple. Can you get the answer?
Yes, sir. I will do it.
Got the answer?
1 minute.
What is it?
No, 1 minute, sir. 1 minute.
Okay. P cos theta is K.
So what is the distance between the two charges, sir?
This length of the string is 1 meter. String length is 1 meter. So this distance is 1 sine 30.
Okay.
So R is 1 sine 30 into 2 of them into 2 because on the other side also. This distance is also there, right? So R will become 1 meter.
Distance between the two particles, sir.
Yeah.
Okay. Half a means it is 1 by
You should know why this is 1 meter.
what, sir?
You should know why it is 1 meter. So the length of the string is 1 meter, right? So this length is 1 sine 30. Okay.
Yes, sir.
So this is also 1 sine 30.
2 sin 30.
Yeah,
Totally.
because it will be symmetric, no? One charge will be here, another charge will
Yes, sir.
be symmetrical in the middle point. So if I divide these two, I get that. 30.
value they haven't given us. Okay. Full I'm getting wrong answers for 0.18.
Okay, I think I'll till next time. Because, I'm getting tan theta is 1 by root 3, right?
Yes,
Then there should be some approximation. 9. Yeah, I think yes, it's more. So it's 15.3. So we do 0.3. Okay, I think the step is correct. You just have to simplify this. So it's actually 1.72. 1.72 to 9 will become 15.3. 15.3. And then here you have 10 raised to minus 1. Yeah. You're getting the answer?
yes, sir.
3, right?
Yes, sir.
Is now electric field work done to rotate by 180 degrees is this one, the approximate separation of charges. Yeah. You're getting the idea here? What is the water molecule? How do you do this one?
I don't know, sir.
No, water molecule. It's a polar molecule, right? So it will act as a dipole. If you place a water molecule in this electric field, there will be some charge separation. Okay, so this is like this is representation of water molecule, and the electric field is this way. Okay, so work done equal to increase in potential energy. Okay, and potential energy is P dot E, right? Minus P dot E. So it's P cos theta. P is constant. E is constant. P is the approximate separation of charges. So P is Q into QA. Okay, rotate by 180 degrees. So P into QA, the electric field E, rotate by 180 from 0 to 0. This will become 2. The voltage is 2.5. So this charge is charge of one electron.
So how the one thing, sir? 1 minus minus 1.
See, now it's rotating by 180 degrees, no? So initially the dipole will be like this in the direction of electric field. And after that, finally the dipole will be rotated like this. Okay, this is one way of rotating by 180 degrees. It is not exactly saying which one. So I'll take the simplest case, 0, and then it's 180 degrees. And for this simplest case, let me get the value. So From this I can get 2. I do not get 8. I just have to get 2A. So it's 2.5 divided by 10 raised to minus 19 into 2 is 2A. So minus 25, it's minus 19, so it's minus 6. 10 raised to minus 6. So 5 by 1.6 into 10 raised to minus 6 meters. There is no 10 raised to minus 6. Oh. Okay. And it's minus 25. That is below. Electric field value I have not put, no. So electric field value is getting divided by it's by E. So electric field value is coming here. So that will give me 10 raised to 4. So 10 raised to minus 10 is fine. So it is 5 by 1.6 into 1.25 into 10 raised to minus 10. So 1.25 into 4 will give me this one. So 4 will go 4 times here, and then it will become 1 by 10. So it's 0.25 into 10 raised to minus 10. 1.25 into 4 times is 5, right? And 5 is 0.25. I made some small mistake. Okay, I'll tell you next time. Electric field is down. It's 1.25. Sorry. It's a 4. It's not 1 by 10. It is 10 on the top, right? It is 10. So it's 10 by 4. 10 by 4 is 5 by 2. It's 2.5. Okay. I'll tell you next time then. Diagram P is placed in non-uniform electric field. So can you answer this one?
No, sir.
Okay, so this is say minus Q and this is plus Q. So the force on this one will be QE1 and this is electric field is non-uniform. I'm just guessing the answer is 1. 45 is 1. 45 is 4. Okay. So electric field here. The net force is Q into E1 by C2. Oh, this is phase variation. Fine. So, okay, this distance is 2A, right? So the electric field here is So E2 is, let me assume its electric field is increasing in this direction. So E1 is E2 plus the distance, that is 2A into 1. So E2 minus E1 is 2A. So the net force is E into 2A, that is P. Forty-five is 1. What? 45 is 4. Okay. So is it clear? Hello? Is it clear?
No, sir. No,
See,
sir.
electric field is non-uniform, right?
Yes, sir.
Okay. So let the minus q be here and plus q be here. And the electric field at this point will be E1 and this here to be E2. It's non-uniform. Okay. So the net force acting on the dipole is this one. Net force. This is clear.
Yes, sir.
Okay. And the electric field is increasing at the rate of 1 volt per meter square. This is actually 1 mole per meter. So it is rate of increase of electric field with respect to space.
Okay.
Okay. So it's 1 volt per meter per meter. 1 volt per meter is unit of electric field. So per meter, how much it is increased? So it's rate of increase of electric field with respect to space. And the distance between these two, it's 2A in this direction. But simplest case, I'll assume this thing is horizontal. Okay. And this thing is also horizontal variation. So the distance between these two is 2A. So for a distance of 2A, the electric field at one point will be more than the other point by the distance 2A into the gradient. The electric field is 1. Okay. So the electric field at one point will be more than the other point by 2E. So the difference is E1 minus E2 is 2A. Okay. So Q into 2A is P.
Yes, sir.
So we have to assume few things like we assume the simplest case of this thing being horizontal and the gradient is along this direction. Okay, so they have to find how much the electric field has changed from one point to another point. So that is 2E. You have previous NEET question bank, right?
Yes, sir.
So fourth chapter I completed. So solve problems from that, or I can send you the sheet, problem sheet. Okay. So how much time you are spending for physics per day?
3 to 4 hours, sir.
Okay, because biology chemistry already studied, no?
But I have to revise it now, sir.
Yeah, but everything
Four-
should revise.
4
Okay, so fine. So should I send the problem sheet or you have problems with you?
I have previous questions, sir.
Okay, solve them and then we can continue. And just a minute. Okay, fine. So we'll meet tomorrow.
Fine, sir. Thank you.
So you have any question?
No, sir.
Okay. Any question?
Yes, sir.
Okay, bye.
Bye, sir.